What is up, everyone? Today we're gonna look at House Robber 2, a medium dynamic programming problem that is heavily inspired by the first installment of the House Robber series. So if you haven't seen that one, I recommend for you to check that out, because we're gonna build upon the solution we figured out in that problem. So let's read the problem. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. All houses at this place are arranged in a circle, which is different from the last problem. That means the first house is the neighbor of the last one. Meanwhile, adjacent houses have a security system connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given a list of non-negative integers representing the amount of money of each house, determine the maximum amount of money you can rob tonight without alerting the police. So we'll head over to Krita and try to draw out a solution, because that's always the first thing you should do before coding. First, you should try to identify all the problem constraints, and then when it's a dynamic programming problem, you should define the recurrence relation, because your code will just be a translation of that. After that, it's always useful to do a complexity analysis to see if your solution actually works, because for any dynamic programming problem, there's many ways to do it. Some are less efficient than others. It all depends on the variables you use in your recurrence. If you have too many dimensions, it's not gonna work. And the last step is always coding. Okay, so let's identify the constraint. So I can do a recap of what we saw in the last video. So for the first problem, there was no circular order of houses, they were all linear. So you didn't have to worry about the first house here being a neighbor of the last one here. And the solution we came up with is, if you ever pick the first house, then you have to skip the next one because it's a neighbor of this one, and go ahead and do the DP for the third house and ongoing to the next houses. Otherwise, if you decided to skip the first house, then you would just eliminate the first house and continue the DP with the rest of the houses. So what that led up to was DP of I equals the max of the two cases we just named. So the first case is the case where you pick and skip, like that. So in that case, it would be nums I plus dp of I plus 2, and the case where you just skip the current house and go to the next one is simply put dp of I plus 1, like this. Now we can actually start working on this problem, because now there's one additional constraint added, is that the first house is a neighbor of the last one. So how could we actually keep track of that? Well, there's a simple way actually, because you could just add a boolean in your DP function, keeping track of if you use the first house. So how that would work would be, instead of just using I as a key in your DP table, you would have DP of I and a boolean here, robbed first. So you keep track of whether you robbed the first house or not. So now you would do the max of the current house well, basically it would be the same thing, but you would add an extra base case. So instead of copying that, you would reuse that, but instead of doing it all the time, you would add an extra base case that if you're at the first house, then you set robbed first to true for all the next calls under it. And then when you reach the last node here, now you check if I is the last house of the array. So you can do that by checking if it's the length of nums minus 1. And the first house was robbed. Then you can't actually use that house, and since you're already at the end of the array, you can simply return 0 because there's no more sub-problems to explore. So here return 0. Ret 0. Okay. So basically this problem was adding that extra constraint to the recurrence relation we defined in the last problem. And let's look at the impacts of this. So we defined the recurrence relation. It's more adding a base case more than changing the recurrence relation, because the rest of the recurrence isn't changed. It's just if I equals 0, well, you pass on the boolean to the children in the call tree. And when you reach the last node, you check if you rob the first node. Now for the complexity analysis. So the trick to do that is count how many possible states there are for each parameter in your DP function and multiply them together. So if we look at DP of I and rob first, well, I can take n multiple values where n is the length of the nums array, because if we're over that range we return 0 and we only treat the values in between. So I is gonna be element of the interval between 0 and n, and being the length of nums. You'll see why I'm doing this, bear with me. And rob first has, so let's put RF for short, is either false or true. So it has two possible states. So now we need to count all the possible combinations between all the possible states to get the total unique number of states for our DP function. And when we memoize, the function will be executed only once for every unique state. So for example, we have 0 false, then we have 0 true, 1 false, so on, so on. So in total it's gonna be n times two possible state. So that gives us a complexity of big O of n. So by just adding the extra constraint of checking if the first house was picked, it effectively doubled the runtime of our algorithm, which is crazy to think about, right? Like just one boolean doubling the runtime, but that's how it is. And now we can look at the code, and you won't be surprised because it's exactly what I defined in the recurrence relation. So here I have my picked first boolean, and I check if I ever get out of the bounds of the array. Well, I return 0 because there's no money to be had there. And now I check if I'm at the last element and I pick the first house, then I can't pick it, so I return 0. And here we have the same recurrence relation as for the first problem, where we either skip the first house, the current house, or we pick it, jump over the next one, and if ever we were on the first house, well, we set the picked first boolean. And by memoizing the function, we're sure of having at most 2n individual calls. And there you have it. It's not optimal in memory because there's more optimal ways to do it, but this is the simplest I can think of. Thank you for watching.